Imagine a point of light so distant it barely registers against the endless black. A star, lost among billions in a spiral arm of the Milky Way. It's lived for millions of years, burning, fusing, holding back collapse with the sheer force of nuclear fire. But now, its fuel is gone. The core, once a furnace of light, begins to cool, and in that instant, the balance shatters. Gravity wins. In less than a second, the heart of the star implodes, not gently, not slowly. It collapses inward at a quarter the speed of light. The outer layers, still unaware, begin to fall. But then, impact. A rebound so violent, so sudden, it triggers a shockwave that rips through the star like a scream through silence. The surface explodes outward in a supernova, brighter than 1 billion suns. For a few weeks, it outshines its entire galaxy. And then, it fades. But something remains. Deep in the wreckage, buried beneath expanding gas and dust, a new object forms. Smaller than a city. Denser than anything you can imagine. A sphere of pure neutrons, no larger than Manhattan, yet weighing more than our sun. It spins once every few seconds. It glows faintly in X-rays. And around it, something begins to build. Something invisible. Something terrifying. A magnetic field. Not like Earth's gentle shield. Not like the sun's shifting loops of plasma. This is different. This is a field so strong, so twisted, so violent that it warps the very fabric of space and time around it. It grows stronger by the millisecond, coiling like a serpent beneath the star's crust. And then, silence. For decades, nothing. Just a quiet, spinning remnant drifting through the void. Invisible. Forgotten. Until the day it wakes up. On December 27, 2004, a pulse of energy crossed 50,000 light-years of space. It came from the constellation Sagittarius. It traveled at the speed of light, 126,000 miles per second. It took 50,000 years to reach us, and when it did, it hit Earth like a hammer. The pulse lasted only 1/5 of a second, but in that fraction of time, it released more energy than the sun emits in 100,000 years. Satellites overloaded, instruments blinded. The Swift Observatory, designed to detect gamma rays from across the universe, shut down automatically. Its sensors flooded. NASA's RHSESE satellite, meant to study solar flares, was swamped. Even the Mars Odyssey orbiter, circling another planet, detected the surge. The wave of radiation passed through the solar system like a ghost, and here on Earth, something strange happened. The upper atmosphere, normally quiet, suddenly ionized. Radio signals bounced differently. The sky, for a brief moment, changed, not visibly, not in color, but in structure, as if the air itself had been shaken. Astronomers looked up, confused, shocked. What could possibly release that much energy in a fraction of a second? A supernova? Too far. A black hole merger? No gravitational waves. A gamma ray burst? Those come from distant galaxies, not our own. Then they traced the signal. It came from a tiny, forgotten star in our galactic backyard. A neutron star, but not just any neutron star. This one was different. It had a magnetic field 1,000 trillion times stronger than Earth's. A field so powerful, it could erase the data on every credit card on the planet, from halfway to the moon. A field so intense, it could rip apart atoms at a distance of hundreds of thousands of kilometers. This was no ordinary star. This was a magnetar. And what we had just witnessed was a starquake. A crack in the crust of a dead star, no bigger than a city, releasing more energy than humanity has ever produced in the blink of an eye. Think about that. A crack. A fracture, a tiny shift in a shell of neutron-rich matter just meters thick. And yet, the magnetic forces beneath it were so immense, so tightly wound, that when it snapped, the entire star rang like a bell, and the energy poured out in a flash of gamma rays so bright it could be seen from across the galaxy. This is not science fiction. This is real. And this is the story of the most magnetic, most violent, most extreme object in the known universe. We've talked about Neutron, stars. We've explored quark stars, hypothetical, exotic, possibly existing in the twilight between neutron matter and pure quark soup. But today, we dive deeper into the heart of a cosmic monster, a star not defined by its mass, not by its gravity, but by something far more invisible, far more dangerous, its magnetic field. Because in the universe, there are forces: gravity, nuclear forces, electromagnetism. And of all of them, magnetism is the one we feel every day, holding fridge magnets, guiding compasses, shielding us from solar wind. But in a magnetar, magnetism isn't just a force. It becomes a law of nature. It bends light. It distorts atoms. It turns the vacuum of space into a strange polarized medium where light splits in two. It can accelerate particles to near light speed. It can trigger explosions without fuel, without fire, just pure magnetic stress. And the craziest part, there are more than 24 known magnetars in our galaxy, and they're all ticking time bombs. Some spin slowly, some fast, some are young, some are old. But all of them share one thing: a magnetic field so strong it defies imagination. So strong that if you were to place a magnetar halfway between the Earth and the Moon, it would wipe every magnetic storage device on the planet. It would scramble pacemakers. It would pull the iron from your blood, atom by atom, before you even knew it was there. But don't worry. The closest known magnetar is over 3,000 light-years away. Still, that 2004 burst? It came from 50,000 light-years away, and it still affected Earth. Imagine one going off in our galactic neighborhood, say 100 light-years away. The burst wouldn't just ionize the atmosphere. It could strip away the ozone layer. It could bathe the planet in radiation. It could trigger mass extinctions. And yet, we wouldn't even see it coming. No warning, no visible flare, just a sudden pulse of invisible energy, gamma rays and X-rays ripping through space at light speed. One moment, silence. The next, chaos. This is not hyperbole. This is physics. And it all starts with a dead star. But not just any dead star. It starts with a massive star, dozens of times heavier than our sun. A giant that burns hot and fast, living only a few million years before its core collapses. When that happens, the outer layers explode in a supernova. The inner core, about 1.4 times the mass of the sun, crushes down into a ball of neutrons, so dense that a single sugar cube-sized chunk would weigh 1 billion tons. That's a neutron star. But a magnetar? That's a neutron star on steroids. It's not just dense. It's not just small. It's not just spinning fast. It's magnetic. And to understand how something like that can exist, we have to go back to the first seconds after the star's death. Because in those first moments when the core is collapsing, spinning, churning like a cosmic blender, something extraordinary happens. A dynamo. Deep inside the newborn neutron star, the super hot, super dense fluid of neutrons and protons begins to swirl. It's rotating hundreds of times per second. Convection currents rise and fall. And as charged particles move, they generate electric currents. those currents create magnetic fields. And those magnetic fields, in turn, influence the motion of the fluid, twisting, amplifying, feeding back on themselves. It's called a dynamo effect. And under just the right conditions, fast spin, strong convection, high conductivity, this dynamo can amplify a magnetic field from ordinary to insane. We're not talking about a few 100,000 Gauss, the strength of an MRI machine. We're talking about 1015 Gauss. That's a quadrillion times stronger than Earth's magnetic field, a number so large it breaks the mind. To put it in perspective, if you took a regular bar magnet and scaled it up to the strength of a magnetar, it would be so powerful that, from a distance of 1,000 kilometers, it could rip the electrons from atoms in your body. It could stop your heart by disrupting the electrical signals in your nerves. It could literally tear matter apart at the atomic level. And this isn't theoretical, this is observed. Astronomers have measured the spin down of these stars, the way they slow over time, and from that, they can calculate the strength of their magnetic fields. And the numbers are off the charts. These stars aren't just neutron stars, they are magnetic monsters, born in violence, living in silence, and dying in bursts of pure energy. And yet, for decades, we had no idea they existed. We knew about pulsars, neutron stars that beam radiation like lighthouses. We knew about X-ray sources. But the idea of a star powered not by rotation or accretion, but by magnetic energy, that was science fiction, until the bursts started. In the 1970s, satellites began detecting strange repeating flashes of gamma rays, short, intense, coming from the same spot in the sky. They called them soft gamma repeaters, SGRs, and no one knew what caused them. Then, in the 1990s, another class of stars was found, anomalous X-ray pulsars. They pulsed in X-rays, but too slowly to be powered by rotation alone. Something else was at work. It wasn't until the 2004 event, the giant flare from SGR 1806-20, that the pieces fell into place. The energy didn't come from spin. It didn't come from accretion. It came from the magnetic field itself. When the crust cracked, the magnetic field shifted. And in that shift, energy was released, not from matter, not from fusion, but from the magnetic field. It was like snapping a rubber band stretched to the breaking point. And the energy, it came from the field. This was the smoking gun. These weren't just weird neutron stars, they were powered by magnetism. And thus the term was born, Magnetar, a star whose energy comes from its magnetic field. A star where magnetism isn't just a feature, it's the engine. And today, we're going to dive into that engine. We're going to explore how such a thing can exist, how it forms, how it behaves, what happens when it explodes, and what it means for our understanding of the universe. Because a magnetar isn't just a star, it's a laboratory. A place where the laws of physics are stretched to their limits, where quantum mechanics and general relativity collide, where matter behaves in ways we can't replicate on Earth. And in that collision, we learn something profound about stars, about matter, about the universe itself. So come with me. Leave behind the familiar sky. Leave behind the sun, the planets, the gentle stars of the night. We're going deeper, into the dark, into the dense, into the heart of a star that died and became something far more powerful, a star that doesn't shine with light, but with magnetism. And as we journey closer, remember this, you are about to witness the most extreme magnetic field in the known universe. And it's real, it's out there, and it's waiting. When a star dies, it doesn't vanish. It transforms. It sheds its outer layers in a final blazing act of cosmic theater, lighting up the sky for thousands of years. But beneath the fireworks, something far stranger remains. Something so dense, so compact, so extreme, that it defies everything we know about matter. This is not the end. This is the beginning of something new. This is what's left when a star dies. Imagine a star massive, hot, brilliant, not like our sun, which will gently fade into a white dwarf. No, this one is different. This is a giant, 20 times the mass of our sun, maybe more. It burns through its fuel in just a few million years, fusing hydrogen into helium, then helium into carbon, oxygen, neon, all the way up to iron. Each stage shorter than the last. Each fusion reaction releasing energy, pushing outward, holding the star up against its own crushing gravity. But iron is the end. Iron doesn't burn. It doesn't release energy. It absorbs it. And the moment the core turns to iron, the balance collapses. The outward pressure from fusion vanishes, and gravity, relentless, unstoppable gravity, wins. In less than a second, the core implodes. It doesn't just shrink, it crushes. Electrons and protons are forced together, merging into neutrons. The entire core, about 1/4 times the mass of our sun, collapses into a sphere, only about 20 kilometers across. That's smaller than most cities. And in that instant, a neutron star is born. Think about that. A star that was once millions of kilometers wide, big enough to swallow entire planetary systems, now compressed into something you could walk across in a few hours. And yet, it still contains more mass than our sun. This is not just dense. This is beyond dense. A single teaspoon of this material, just 5 milliliters, would weigh 2 billion tons. That's like stacking every single car ever built on Earth and then multiplying that by 1,000. And it's all packed into the size of a spoon. But how? It all comes down to one force: gravity. When the core collapses, there's nothing left to stop it. No fusion. No pressure, just gravity pulling everything inward. The atoms themselves are destroyed. Electrons, which normally keep atoms apart, are shoved into protons, turning them into neutrons. And those neutrons are packed together so tightly that they're touching, like marbles in a jar, but with no space between them. This is neutron matter. It's not like anything on Earth. It's not solid. It's not liquid, it's not gas. It's something in between, something physicists call neutron degenerate matter, a state of matter so extreme it only exists in the hearts of dead stars. And within this strange substance, something else begins to happen. The newborn neutron star is spinning fast, because the original star was rotating, and when it collapses, that rotation speeds up. It's the same principle as a figure skater pulling in their arms to spin faster. Only here, the effect is unimaginable. A star that once rotated once every few weeks now spins hundreds of times per second. And as it spins, it emits beams of radiation, radio waves, X-rays, gamma rays, shooting out from its magnetic poles. If those beams sweep across Earth, we see them as pulses, regular, precise, like a cosmic clock. We call these objects pulsars. They were discovered in 1967, and for a brief moment, scientists wondered if they were signals from aliens. The pulses were that regular. But soon the truth emerged. These were rapidly spinning neutron stars, lighthouses in the dark. But not all neutron stars are the same. Some spin slowly, some are quiet. Some are hidden in binary systems, feeding off a companion star. But all of them share the same origin, the violent death of a massive star. And yet, among them, a rare few are different. Not because they're heavier, not because they're bigger, but because of something far more invisible, something far more powerful, their magnetic field. You see, every neutron star has a magnetic field. It's a remnant of the original star's magnetism, frozen into the core during collapse. But in most cases, it's normal. If anything about a neutron star can be called normal, we're talking about a field 100 trillion times stronger than Earth's. Strong enough to pull iron from your blood at close range. Strong enough to distort atoms. But in a special few, something extraordinary happens. The magnetic field doesn't just survive the collapse, it explodes in strength. Amplified by the star's rapid rotation and internal turbulence, the field grows 1,000 times, stronger, reaching levels that break the laws of physics as we know them. And when that happens, a neutron star becomes something else. It becomes a magnetar. But to understand how rare and extreme this is, we have to look at the numbers. Out of all the neutron stars in the galaxy estimated to be over 100 million, only about 30 have been confirmed as magnetars. That's 1 in every few million. And even among those, only a handful are active, emitting bursts, flares, or pulses that we can detect. The rest, they're silent, hidden, waiting. But why are magnetars so rare? Because their birth requires a perfect storm. First, the original star must be massive enough to form a neutron star, but not so massive that it collapses directly into a black hole. Second, it must be spinning very fast before it dies. This rapid rotation fuels the internal dynamo, the engine that amplifies the magnetic field. Third, the core must be turbulent, hot, convecting, like a pot of boiling water, but with neutron fluid moving at incredible speeds. And in those first few seconds after collapse, when the star is still hot and fluid, the dynamo kicks in. Charged particles swirl, magnetic fields twist, and through a process called the alpha-omega dynamo, the field is amplified from strong to unimaginable. It's like taking a small magnet and running it through a cosmic amplifier, turning it into a force so powerful it dominates the star's entire existence. And once that field is set, it's locked in. Because neutron stars have a crust, a solid shell of atomic nuclei and electrons, just a few meters thick but incredibly strong. And as the star cools, that crust stiffens, freezing the magnetic field in place. So the field doesn't fade quickly. It stays strong for thousands of years, and during that time, it does something incredible. It powers the star. Most neutron stars shine because they're spinning. Their rotation generates energy, which is radiated away as beams or heat. But in a magnetar, the energy doesn't come from spin. It comes from the magnetic field itself. As the field slowly decays or suddenly shifts, it releases enormous amounts of energy, sometimes gradually, sometimes explosively. And that's when we see them, not as steady pulsars, not as quiet X-ray sources, but as flares, as bursts, as giant eruptions that light up the galaxy. And when that happens, we know a magnetar has awakened. But what does one actually look like? Not like a normal star. There's no surface fusion, no glowing plasma, no visible light. Most magnetars are dark. They don't shine in the way our eyes understand. Instead, they glow faintly in X-rays, the kind of light we can only see with space telescopes. And sometimes, when they flare, they emit gamma rays, the most energetic light in the universe. And even then, they're not bright for long. A giant flare might last a fraction of a second. A burst might repeat over hours. But the star itself, It's just a tiny, dense sphere, spinning slowly, wrapped in a magnetic field so strong it warps the vacuum of space. And yet, it's alive, not in the biological sense, but in the cosmic sense. It breathes in magnetic energy. It quakes under internal stress. It pulses with radiation. It is, in every way, a living relic of a dead star. And of all the neutron stars in the galaxy, Magnetars are the most extreme. They spin slower than pulsars, some only once every few seconds. That's because their immense magnetic fields act like brakes, slowing them down over time. The stronger the field, the faster the spin down. They don't have accretion disks because their magnetic fields are so strong they push away any infalling matter. No fuel, no glow from outside, just internal magnetic energy, and they don't live long on cosmic timescales. After about 10,000 years, their magnetic fields weaken enough that they go quiet. No more flares, no more bursts. They become invisible. Just another cold, dead neutron star drifting through space. But while they're active, they are the most violent, most energetic, most magnetic objects in the known universe. And they are not theoretical. They are real. We've seen them. We've measured them. We've felt their influence across 50,000 light years. And every time one flares, we learn something new. Because a magnetar isn't just a star, it's a laboratory, a place where matter is squeezed beyond comprehension, where magnetic fields dominate everything, where the laws of physics are stretched to their breaking point. And in that extreme environment, we find clues to questions we've been asking for centuries. What happens when matter is compressed to nuclear density? How do magnetic fields behave at strengths we can't replicate on Earth? Can we see? Quantum effects on a stellar scale. And perhaps most importantly, how many more are out there? Because we've only found a few dozen, but the galaxy is vast. And if even 1 in 100 neutron stars becomes a magnetar, there could be hundreds of thousands hiding in the dark, waiting, silent, until the day they crack. And when they do, the universe takes notice. So the next time you look up at the night sky, remember this. Among the quiet stars, there are remnants, dead stars, neutron stars, pulsars, and among them, a rare few so rare, so extreme, that they don't just spin, they explode with magnetism. They don't shine with light, they burn with magnetic energy. They're not powered by fusion, they are powered by the strongest force in the cosmos. And they are called Magnetars. There is a moment, just after a massive star dies, when the universe holds its breath. The core has collapsed. The outer layers have exploded. The neutron star has formed. It spins, it glows, it pulses. But it is not yet a magnetar. Not yet. Because in those first few seconds, before the crust solidifies, before the star cools, before the magnetic field locks in, something extraordinary happens. Something so violent, so turbulent, so perfectly chaotic that it transforms a neutron star into something far more extreme. It begins with spin. The original star was rotating, slowly perhaps, over weeks or months. But when it collapses from millions of kilometers down to just 20, that rotation accelerates dramatically. Like a figure skater pulling in their arms, the core spins faster and faster. In the first second after collapse, it may be rotating hundreds of times per second. But spin alone isn't enough. What matters is what happens inside. Deep within the newborn neutron star, the core is not solid. Not yet. It's a super-hot, ultra-dense fluid, mostly neutrons, but also protons and electrons, swirling in violent convection currents. The temperature is over 1 billion degrees. The density is beyond comprehension. And the fluid is moving, rising, falling, twisting, like a storm trapped in a sphere the size of a city. This is not calm matter. This is cosmic turbulence. And in that chaos, something begins to grow, an electric current. Because protons and electrons are charged, and when charged particles move, they generate magnetic fields. And when those fields interact with the fluid motion, they create feedback loops, fields that twist, stretch, and amplify. This is the dynamo effect. On Earth, our magnetic field is generated by a dynamo in the molten outer core, liquid iron moving around a solid inner core, driven by heat and rotation. It's slow, it's steady, it takes thousands of years to change. But in a newborn neutron star, the dynamo is violent. It operates on timescales of seconds, and the conditions are perfect. Fast rotation, intense convection, high electrical conductivity. These are the ingredients for magnetic amplification on a scale we can barely imagine. Think of it like a generator, but one that doesn't run on steam or water. It runs on gravity, heat, and motion. As the fluid swirls, it stretches magnetic field lines. Some are twisted into spirals, others are folded back on themselves, and with each turn, the field gets stronger. This is called flux amplification, the process by which a weak magnetic field becomes an ultra-strong one. And in the right conditions, it can increase by a factor of 1,000 in less than a minute. But how? Let's break it down. Imagine the neutron star's interior as 2 layers, an outer region where convection dominates, and an inner region where rotation is smooth and fast. This is the alpha-omega dynamo, a theoretical engine that astrophysicists believe powers the most extreme magnetic fields in the universe. The omega part comes from the star's rapid rotation. It twists the magnetic field lines around the equator, turning them into a toroidal field, a donut-shaped field wrapped around the star's middle. The alpha part comes from convection. Rising and falling blobs of fluid, driven by heat, twist those toroidal fields into poloidal fields, loops that go from pole to pole. And when you combine them, twisting and folding over and over, the magnetic field grows exponentially. It's like a feedback loop from hell. Each twist strengthens the field, each fold concentrates it, and because the fluid is so conductive, the field doesn't dissipate. It gets trapped, amplified, locked in. And in less than 10 seconds, what started as a magnetic field 100 trillion times stronger than Earth's becomes a field 1,000 times stronger, a quadrillion times Earth's, 10^-9115 Gauss. And that, right there, is the birth of a magnetar. But this doesn't happen to every neutron star. Only the rare ones, only the ones born spinning fast over 500 times per second, only the ones with strong convection, hot cores churning like a pressure cooker, only the ones where the dynamo has time to work before the star cools and the crust forms. Because once the crust sets just minutes after collapse, the dynamo shuts down, the fluid slows, the convection stops, the core begins to solidify, and the magnetic field, it freezes in place, no longer growing, no longer changing, just locked, trapped in a shell of neutron-rich matter, meters thick under unimaginable pressure. And from that moment on, the star is no longer powered by rotation. It is powered by magnetism. This is what makes a magnetar different. Not its mass, not its size, not its spin, its magnetic energy. While a pulsar shines because it's spinning, A magnetar glows because its magnetic field is decaying, slowly releasing energy over thousands of years. And sometimes, when the field shifts suddenly, that energy is released in a burst so powerful it can be seen across the galaxy. But here's the terrifying part. We can't predict which neutron stars will become magnetars. We can't see the dynamo at work. It happens in the first seconds, hidden beneath the supernova's glare, buried in radiation, invisible to our telescopes. All we see is the aftermath. A star that spins too slowly for its age. A star that flares without warning. A star that emits more energy in a fraction of a second than the Sun does in centuries. And when we measure its magnetic field by how fast it's slowing down, by the energy of its bursts, we realize this is no ordinary neutron star. This is a magnetic monster, and its power comes from a process so extreme, so perfectly tuned, that it only works once in a million stars. But let's go deeper. What does a magnetic field of 10.515 Gauss actually do? To understand that, we have to leave behind the world of classical physics. We have to enter the realm of quantum electrodynamics, the physics of light and matter at the smallest scales. Because at these field strengths, the vacuum of space itself stops behaving normally. Normally, empty space is empty. A void, a stage where particles move, but the stage itself is passive. But in the presence of a magnetar's field, the vacuum becomes active. It becomes polarized. Virtual particles, pairs of electrons and positrons that constantly pop in and out of existence, begin to align with the object of existence, magnetic field. The vacuum develops a kind of structure. It starts to split light. Yes, light. Photons traveling through the magnetar's magnetosphere don't just bend, they split into two. This is called vacuum birefringence, a phenomenon predicted by quantum theory, but only observable in the most extreme magnetic fields. And in 2016, astronomers detected signs of it near a neutron star. Strong evidence that such fields really do warp the fabric of reality. Near a magnetar, light doesn't travel in straight lines. It doesn't even travel as a single beam. It fractures. It polarizes. It behaves in ways that defy classical optics. And that's just the beginning. Atoms themselves are distorted. Under normal conditions, atoms are spherical electrons orbiting in clouds around a nucleus. But in a magnetar's field, those clouds are stretched into thin needles, aligned with the field like iron filings near a magnet. Hydrogen atoms become cylindrical. Electron orbitals are compressed in one direction, elongated in another. And if you could somehow get close within a few hundred kilometers, the magnetic force on the iron in your blood would be stronger than the chemical bonds holding your hemoglobin together. You wouldn't just die, you'd be unmade atom by atom before you even realized what was happening. And yet, the magnetar itself holds together. Because its gravity is immense, a single sugar cube-sized piece weighs 1 billion tons, and its crust, though only meters thick, is stronger than any material on Earth. It's made of nuclear pasta, a bizarre state of matter where atomic nuclei are squeezed into shapes like sheets, tubes, and bubbles, forming the strongest material in the universe. But even that crust has limits, because beneath it, the magnetic field is still alive, still shifting, still building stress. And when the tension becomes too great, the crust cracks. This is a starquake, a seismic event on a stellar scale, not like an earthquake where tectonic plates shift. This is the entire surface of a city-sized star fracturing in seconds, and when it happens, the magnetic Field twisted and stressed snaps into a new configuration, like a rubber band that's been wound too tight and finally breaks. And in that instant, energy is released, not from nuclear fusion, not from accretion, not from rotation, from the magnetic field itself. This is the source of the giant flares. The soft gamma repeaters, the bursts that blind satellites and shake the Earth's atmosphere. And the energy. It comes from the field's stored energy. Energy that was built up over seconds, in the first moments after collapse. So in a way, every magnetar flare is a relic of the star's birth. A delayed explosion. A cosmic echo of the dynamo that created it. And when we detect one like, the 2004 giant flare from SGR 1806-2000, we're not just seeing a starquake, we're witnessing the final release of energy from a process that began 50,000 years ago. In that sense, a magnetar is not just a star, it is a time capsule, a frozen moment of cosmic violence. A magnetic storm trapped in a sphere of neutron matter. And every burst is a reminder, this star didn't just die. It became something far more powerful. It became a generator of extreme physics, a place where the laws of nature are rewritten, where light splits, where atoms deform, where the vacuum of space becomes a strange, structured medium, and where, for a brief moment, the universe shows us what it's truly capable of. So, the next time you think about a dead star, don't just imagine silence. Imagine turbulence. Imagine spin. Imagine a storm in the core of a city-sized object, amplifying a magnetic field beyond comprehension. Because that, right there, is the moment a neutron star becomes the monster. That is the birth of a magnetar. And it happens in the dark, in the first seconds, in the heart of a dying star. And we're only beginning to understand it. Close your eyes. Imagine you're floating in space, not near Earth, not near the sun. You're deep in the galactic plane. The stars are distant. The sky is black. And ahead of you, just a few hundred kilometers away, is a sphere no larger than a city. Dark, silent, spinning slowly. It doesn't glow like a star. No fire, no fusion, no visible light. But something is wrong. The space around it bends. Not from gravity, though that is immense. No, this is different. It's the magnetic field. And you can't see it. You can't hear it. But you feel it. Because the moment you cross a certain boundary, say 1,000 kilometers from the surface, your body begins to change. Not metaphorically. Not slowly. Instantly. The iron in your blood, bound in hemoglobin, carrying oxygen from your lungs to your cells, is no longer just the molecule. It is now a magnetic dipole. And the field around you, measuring over a quadrillion Gauss, is stronger than any force your body has ever encountered. It doesn't pull, it doesn't push, it aligns. Every iron atom in your bloodstream snaps into place, like tiny compass needles all pointing the same way. The hemoglobin molecules distort. Their structure fails. The chemical bonds weaken. And then, silently, invisibly, your blood begins to tear itself apart. But that's not the worst of it. Your nerves, your brain rely on electric currents. Ions moving across cell membranes, sodium, potassium, calcium, these are charged particles, and in a magnetic field this strong, their motion is no longer free. It is constrained. The field forces charged particles to spiral along its lines, like beads on a wire. They can't move sideways. They can't jump. They're trapped. So when a nerve signal tries to fire, when your brain sends the command to move, to breathe, to scream, the signal fails. Your nervous system shuts down, not from damage, from physics. And still, you're not dead, not yet, because the destruction is just. Beginning. Now consider your atoms. Under normal conditions, atoms are roughly spherical. Electrons orbit the nucleus in clouds, probability zones where particles might be. But in a field this strong, those clouds collapse. The magnetic force overwhelms the electrostatic force that holds atoms together. Electrons are squeezed into narrow cylinders, elongated along the direction of the field, compressed across it. Hydrogen, the simplest atom, becomes a needle, a long, thin filament of charge. Molecules, they can't form. Chemistry, it stops. The very idea of matter as we know it, solid, liquid, gas, plasma, breaks down. This is no longer chemistry. This is quantum mechanics under siege. And if you could somehow survive all this, if your body were magically held together, your eyes would see something even more impossible. Light doesn't behave normally. Because near a magnetar, the vacuum of space itself becomes a strange medium. Empty space, what we think of as nothing, is not truly empty. It's a seething foam of virtual particles, electrons and positrons blinking in and out of existence, borrowing energy from the universe and vanishing in a fraction of a second. But in a magnetic field this strong, those virtual particles don't just appear and disappear. They align. They form a kind of structure. And when photons, particles of light, pass through this structured vacuum, they don't travel in a single path. They split. This is called vacuum birefringence, a phenomenon predicted by quantum electrodynamics, but only possible in the most extreme conditions. Near a magnetar, a single beam of light entering the magnetosphere divides into two, one component polarized parallel to the magnetic field, the other perpendicular. They travel at slightly different speeds. They bend in different ways. So, if you could shine a flashlight toward a magnetar, the beam wouldn't just curve, it would fracture, splitting into two ghostly rays, drifting apart as they approach the surface. And if you could see X-rays, high-energy light emitted by the star, you'd witness something even stranger. The light would be polarized, twisted by the field, carrying information about the magnetic architecture of the star. In fact, in 2016, astronomers observed this exact effect near a neutron star, RxJ 1856.53754, detecting polarized X-rays that could only be explained by vacuum birefringence. It was the first observational hint that Einstein and Heisenberg were right. In the presence of extreme fields, empty space is not empty. It has properties. It can bend light. It can spit photons. And near a magnetar, it becomes a cosmic lens, distorting reality itself. But let's go deeper. What if you weren't just near a magnetar? What if you were on it? Impossible, of course. No material could survive. No spacecraft could land. But hypothetically, what would you see? First, the gravity. Even though the star is small, its mass is greater than the Sun's. The surface gravity is about 100 billion times stronger than Earth's. If you stepped onto it, you'd weigh billions of tons. You'd be flattened instantly, reduced to a thin layer of atoms, smeared across the crust like dust. But again, hypothetically, let's say you're protected. You look down. The ground beneath you isn't rock. It isn't metal. It's nuclear matter. The crust of a magnetar is only a few meters thick, but it's the strongest material in the known universe. It's made of nuclear pasta, a bizarre state of matter where atomic nuclei are squeezed into shapes like sheets, gnocchi, tubes, spaghetti, and bubbles, lasagna, arranged in a lattice under unimaginable pressure. This crust is so strong, it can store immense stress like a spring wound too tight, and beneath it, a superfluid ocean of neutrons. No atoms, no molecules, just a sea of neutrons flowing without friction, swirling in vortices that never stop. And at the very center, we don't know. Possibly a core of quark matter, all the strange matter, or something even more exotic. But whatever it is, it's wrapped in a magnetic field so strong it dominates everything. It doesn't just influence particles, it rewrites the rules. In this environment, the electromagnetic force, the same force that holds your body together, that powers your phone, that makes fire burn, becomes the master of reality. It overpowers the strong nuclear force in some regions. It distorts the weak force. It makes gravity look weak by comparison. And when the crust finally cracks, when the magnetic stress becomes too great, what happens is not just an explosion, it is a reconfiguration of space-time. A starquake, a fracture in the crust, maybe just a few meters long, releases energy equivalent to a magnitude 32 earthquake. The entire star vibrates. The magnetic field shifts. And in that shift, a burst of gamma rays erupts so intense it can be detected 50,000 light-years away. And all of it, every flash, every burst, every pulse, comes from magnetic energy. Not fusion, not gravity, not motion. Magnetism. This is what makes a magnetar unique. It is the only known object in the universe where magnetism is the primary energy source, where the field doesn't just influence behavior, it powers the star. And in doing so, it creates conditions we cannot replicate on Earth. We can't build a magnet that strong. We can't compress matter that densely. We can't heat a plasma to 1 billion degrees and hold it in place. But nature did, in the heart of a dead star. And by studying magnetars, we're not just learning about exotic stars. We're probing the fundamental laws of physics. We're testing quantum electrodynamics in ways we never could in a lab. We're seeing how matter behaves when pushed beyond its limits. We're watching the vacuum of space itself become a dynamic medium. And we're realizing something profound. The universe doesn't just follow the laws of physics. Sometimes it breaks them, or rather reveals that the laws are deeper, stranger, and more beautiful than we ever imagined. So the next time you think of a star, don't just picture a ball of fire. Picture a magnetic storm frozen in neutron matter. Picture a cracked crust holding back a quadrillion Gauss field. Picture a vacuum that splits light like a prism. Picture a place where atoms are needles, where nerves fail, where space itself is polarized. Because that place exists, it is real, and it is called a magnetar. Stand near one. Just for a moment, you wouldn't see a star. You'd see the edge of reality. We don't need to travel 50,000 light-years to feel the power of a magnetar. It has already reached us. Not with fire, not with debris, but with light, invisible light. Gamma rays, X-rays. A pulse so intense, so sudden, it left a mark on our planet, on our satellites, our atmosphere, even our understanding of the cosmos. That moment came on December 27th, 2004. At 21,000 Universal Time, a wave of energy swept through the solar system. It came from the constellation Sagittarius, deep in the heart of the Milky Way. It traveled at the speed of light. It took 50,000 years to reach us, and when it did, it hit like a cosmic thunderclap. The source? A star so small, so dark, it wasn't even visible in optical telescopes. Its name is SGR 1806-20, a soft gamma repeater, one of the rarest and most powerful objects in the galaxy. And what we witnessed was not a supernova, not a black hole merger, not a distant gamma ray burst from the edge of the universe. It was a starquake, a crack in the crust of a magnetar just a few meters long, releasing more energy in 1/10 of a second than the sun emits in 100,000 years. The burst was so powerful it ionized Earth's upper atmosphere. Radio signals bounced differently. The ionosphere, normally stable, became turbulent. Satellites overloaded. NASA's RHSE observatory, designed to study solar flares, went into safe mode. The Swift satellite, built to detect gamma-ray bursts across the universe, was completely saturated, blinded by a source within our own galaxy. Even the Mars Odyssey orbiter, circling another planet, detected the surge. From over 100 million miles away, it recorded a spike in radiation. This was not a near miss. This was a direct hit. And yet, no one saw it coming. No visible warning, no brightening star, no expanding nebula, just silence. Then flash. And in that flash, we learned something terrifying. Magnetars aren't just distant curiosities. They are here, in our galaxy, and they are active. SGR 1D6-20 is located about 50,000 light-years away, on the far side of the Milky Way. It's part of a rare group of stars, a young, massive star cluster that includes one of the most luminous blue variables known. But the magnetar itself is invisible. It doesn't shine, it doesn't burn. It only pulses in X-rays, and occasionally it explodes. And when it does, the entire galaxy takes notice. The 2004 flare was classified as a giant flare, a rare event seen only 3 times in history: 1979, 1998, and now 2004. Each one came from a different magnetar. Each one was more powerful than anything our sun could produce. But SGR 1806-2T's burst was the brightest ever recorded. For a fraction of a second, it became the brightest object ever seen in the night sky. If we could see gamma rays, it outshone everything, every star, every star, every star, every star, every star, galaxy, every quasar. And then, just as quickly, it faded. But the data remained. And from that data, astronomers calculated the true scale of the event. The energy released? 10 ed 46 ergs. That's a 10 followed by 46 zeros. To put that in perspective, if you converted the entire mass of Mount Everest into pure energy via Einstein's mChNe, you'd get about 10 ChNe CO44 ergs. This flare released 100 times more, and it came from a star smaller than Manhattan. This wasn't just an explosion, it was a cosmic tantrum, a release of magnetic stress built up over decades, maybe centuries. And it wasn't unique. We've seen other magnetars act up. Take SGR 1900+14. In 1998, it erupted with a giant flare so bright it temporarily blinded the Compton Gamma Ray Observatory. It's located about 20,000 light-years away in the constellation Aquila. And like SGR 106-20, it's a soft gamma repeater, emitting random bursts of gamma rays, sometimes multiple times a day. Or 1E248.15937, a magnetar in the southern sky, known for its slow spin and strong X-ray pulses. It's one of the few magnetars we studied in detail, watching how it slows down over time, how its magnetic field decays, how it occasionally flares. And then there's Swift J18118.0-67. Discovered in 2020 by the Swift satellite, this is one of the youngest known. Magnetars possibly only 240 years old. It spins once every 14 seconds, which is fast for a magnetar. It's also one of the closest, just 16,000 light-years away. That's practically in our backyard. And it's active. It flares. It pulses. It may one day unleash a giant flare of its own, and if it does, we'll feel it. Not catastrophically. 16,000 light-years is still far enough to spare us from atmospheric collapse or mass extinction. But we'll detect it. Our satellites will register the surge. Our telescopes will point. Our scientists will scramble. Because when a magnetar flares, it doesn't just emit gamma rays. Sometimes it emits something even more mysterious. Fast radio bursts. These are millisecond-long pulses of radio waves, so bright they can be seen across billions of light-years. For years, their origin was unknown. Aliens, black holes, neutron star collisions. But in 2020, something changed. Astronomers detected a fast radio burst, FRB 2004-288, coming from the same direction as SGR 1935 plus 2005-4, a known magnetar in our galaxy. And the timing matched. For the first time, we had direct evidence, at least some fast. Radio bursts come from magnetars, not from distant galaxies, not from exotic physics, from a starquake, a magnetic reconnection event, releasing a burst of coherent radio waves that blasted across space. This was huge. It meant that the universe's most mysterious radio signals might have a relatively local explanation, and it meant that magnetars are even more powerful than we thought. They don't just flare in gamma rays, they can light up the radio sky in a flash. But here's the real question. How many more are out there? We've confirmed about 30 magnetars in the Milky Way. But estimates suggest there could be hundreds of thousands. Because magnetars don't live long, only about 10,000 years before their magnetic fields weaken and they go quiet. So the ones we see are just the active minority. The rest? They're invisible, cold, dark, drifting, waiting, and some may be much closer than we think. The closest known magnetar is 1E 1048.145937, about 9,000 light-years away. Still distant. But if one existed within 1,000 light-years, say in a nearby star-forming region, and it erupted with a giant flare, the consequences could be severe. A burst from that distance could strip part of the ozone layer. It could bathe the planet in radiation. It could trigger auroras worldwide. It could disrupt satellites, power grids, communication. We wouldn't be destroyed, but we'd know, without a doubt, that we live in a dangerous galaxy. And yet, we're not defenseless. Every time a magnetar flares, we learn. We map its location. We measure its field, we decode its signals, and with each burst, we get closer to understanding not just magnetars, but the extreme physics they embody. They are natural laboratories, probing quantum electrodynamics, testing general relativity, revealing how matter behaves under conditions we can't replicate on Earth. And they remind us of something fundamental. The universe is not just vast, it is violent, it is unpredictable, and it is alive in ways we're only beginning to understand. So the next time you look up at the night sky, remember, among the quiet stars, there are sleeping monsters. Tiny, dense, silent, but when they wake, the whole galaxy hears it, and we on our small blue world feel the echo. We began this journey in silence, with a star collapsing, a core imploding, a magnetic field awakening in the dark. And now we stand at the edge, not of space, but of understanding. Because magnetars are not just cosmic curiosities, they are revelations. They're not just the most magnetic objects in the universe. They are teachers. They show us what happens when matter is crushed beyond recognition, when magnetic fields dominate gravity, when the vacuum of space itself stops being empty and starts behaving like a crystal. They are laboratories of extreme physics, places where the laws we learned in textbooks are stretched, twisted, and sometimes broken. And in that breaking, we find truth. Because every time a magnetar flares, it doesn't just release energy, it releases information. It tells us about the behavior of neutron matter, about the strength of magnetic fields, about the way quantum mechanics and general relativity intersect in the most violent corners of the cosmos. And perhaps most humbling of all, it reminds us how little we know. We still don't understand what happens at the very center of a magnetar. Is it pure neutrons, a soup of quarks, something even stranger like strange matter, or a Bose, Einstein condensate of exotic particles? We don't know how long magnetars truly live. We can't predict when they'll flare. We can't replicate their conditions on Earth, but we can observe, we can measure, we can wonder. And that, more than anything, is what drives science, not certainty, but curiosity. The same curiosity that made early humans look up and ask, what are those lights in the sky? The same curiosity that led Galileo to point a telescope at Jupiter, that made Einstein question time and space, that pushed us to build orbiting observatories, to listen to the radio whispers of distant stars, to decode the language of gamma rays and X-rays. And now that curiosity has brought us here, to a city-sized star, spinning in silence, holding a magnetic field so strong it can shake the fabric of reality. And we are listening. We are learning. Because magnetars aren't just monsters, they are keys. Keys to understanding the life and death of stars. Keys to probing the nature of matter at nuclear density. Keys to testing quantum electrodynamics in ways no earthbound lab ever could. And they may even hold clues to the biggest mysteries of all. Like fast radio bursts, those millisecond flashes that come from across the universe. We now know some come from magnetars. But what about the others? Are they from magnetars in distant galaxies? From mergers? From something we haven't even imagined? And what about gravitational waves? When a magnetar cracks, when its crust shifts in a starquake, it should send ripples through space-time. Tiny, perhaps, but detectable one day with sensitive enough instruments. Will we one day hear the ringing of a magnetar like a bell struck in the dark? And could those ripples tell us about the star's internal structure, its density, its magnetic field? Possibly, because in the universe, every extreme is an opportunity. Every explosion, every burst, every silent pulse is a message, and we are finally learning how to read them. But let's go deeper. What do magnetars teach us about our place in the cosmos? That we live in a universe that is not gentle, not static, not predictable. We live in a universe where stars explode, where black holes devour, where magnetic fields can rip atoms apart, and yet here we are, alive, aware, capable of understanding. We are made of stardust, yes, but we are also made of questions, and that makes us unique, because we don't just exist in this universe. We observe it, we decode it, we name its wonders. We call them neutron stars, quark stars, pulsars, magnetars. And in doing so, we bring order to chaos. We turn fear into fascination. We turn the unknown into knowledge. And every time we detect a magnetar flare, Whether from 50,000 light years away or right here in our galaxy, we are reminded the universe is not just vast. It is alive, pulsing, exploding, evolving, and we are part of it, not separate, not above, but within, connected by the same physics, the same forces, the same stardust. And one day, if we survive long enough, we may even learn to use that knowledge, to harness extreme physics, to explore the stars, to build instruments that can withstand magnetic fields 1 trillion times stronger than Earth's, to visit, not just in thought, but in reality, the most extreme places in the cosmos. But for now, we watch, we listen, we wonder, and we keep building better telescopes, better detectors, better minds, because the story of the Magnetar is not just about a dead star, it's about what happens when nature goes to the extreme. And it's about what happens when intelligence meets the unknown. We started with a star dying in silence. Now we end with a call to look up, to keep exploring, to fund science, to support astronomers, physicists, engineers, those who spend their lives decoding the universe's most subtle signals, because the next burst could come at any time, from any direction, and when it does, we must be ready to record it, to study it, to learn from it, because in that flash of gamma rays, in that ripple of radio waves, there may be a clue to how matter behaves under impossible pressure, to how magnetic fields shape galaxies, to how the universe began, to how it will end, and perhaps, just perhaps, to how we fit into it all. So the next time you see the night sky, don't just see stars. See stories, see violence, see beauty, see mystery, and see hope. Because as long as there are magnetars in the dark, spinning, cracking, flaring, we have something to learn. And as long as we have eyes to look, minds to question, and hearts to wonder, we are not lost. We are on a journey, and the universe, it's waiting, not to destroy us, but to be understood. So keep watching the sky, keep asking questions, keep seeking the truth. Because the most powerful force in the universe isn't gravity, isn't magnetism, it's curiosity, and it lives in you.